the kernel. We're going to make a system call, get process ID. It's a common system call, but we really cannot call this in OpenBSD because we didn't know where it is. We cannot, if we are in the interruption 80, we cannot call the interruption 80. Or maybe we can, but we didn't realize how we could make a reentrant or interruption.
Just call the previous interrupt vector. Call the previous interrupt vector. You want to override.
Yes, I tried that, but when we called the previous interrupt vector, the OpenBSD kernel just crashed. Just say that the stack is bad, and in fact crashes in a weird way. In a little weird way, it was saying that the interruption was a kind of a Linux interruption. I crashed it. I tried a lot. I tried trying to fix the stack to make the OpenBSD kernel thinks that is a common interruption, but it didn't not work. I'm trying to jump directly to the get process ID function. That did not work either. In fact, I was saying maybe it's a way to do it. Maybe it was some little part that I was missing, but really could not make it work. Couldn't call directly a system call in the kernel. And in fact, it's a much easier way to do it. I really don't need to call this particular system call because we can read the process directly from the memory. I would like to know how call a system call from inside a system call. That will make this exploit a lot easier. So, how we must find the process ID. So, first we must find the process ID is a memory structure is in somewhere in the memory. Somewhere? Yes. I'm sorry.
How do you prevent, because you're basically using a buffer, an mbuff to host the interrupt handler
yes.
for the interrupt.
Exactly.
How do you prevent the system to free that mbuff that you're using and to be reused and be never written with your data?
Yes, it's because we are doing this that's a nice question. I was saving that for the end. But okay, no, it's no problem. This happened a lot faster. The system really don't have time to free that buffer. And in my experience, the buffer can be allocated a lot of times in memory. This happens in a couple of microseconds, and the buffer can be for hours in memory unallocated. In my experience, I don't know why I was saying I really don't know the internal working of the OpenBSD kernel, but the mbuff remains a lot of time allocated in memory, so we got plenty of time to place the interruption vector in the same mbuff. We could reserve some memory or map some pages in unallocated pages and jump there. But in fact, that was not necessary. I was thinking, this is going to be a lot difficult. We must map some part of the memory, unused, but it was not necessary because it worked right away. Worked like, 90%, 99% of the times. So, but this is it's an excellent question. So we are hooking the interruption vector, and we must find if the process calling us is root, because we want to override. We want to take over a process that got root privileges. First, we find the current process variable. The current process variable is in fact something like an array, because OpenBSD is multiprocessor. It's placed in somewhere of the memory. It can change for kernel from kernel. Is placed in a static position of the memory. We must find it. How we find the current process variable? Well, we basically we search for a pattern of memory. We are searching. We have a lot of kernel exploit using this technique, that is search for a pattern, because we can do much else. We find a pattern that never changed in OpenBSD in like 10 years. We found a function that is an assembly function never changed in 10 years, and we found exactly that pattern. We searched for that pattern and found it. We know that the current process variable is an offset from that pattern. So in this way, we found the current process variable. When we got the current process variable, we know a lot of info about the process that are calling us. We know that, for example, the user ID that owns the process. With the user ID, we know if the process is root or not. So we basically do it all by hand, let's say. We search in the memory. And what's happening if the user is root? Well, we must take over the process, because we now know that we got a process with all the privilege. So first we must take down a protection of the OpenBSD kernel. We must think, well, now we know that the process calling off is root. We can simply write in the return pointer. We know the return pointer of the interruption is in the stack. So we simply overwrite this and make the kernel to return to our code in the user, in ring 3 and in user mode. But this is not good, because maybe the process, the function that are calling us is, let's say, libc, or an important library of the system. If we overwrite the binary that are calling us, we are breaking all the system. So we must jump. The best idea that occurred to us was to try to overwrite the stack, to try to execute code in the stack, because we know that the stack is one for every process, and if we overwrite the stack, we must leave all the other process alone. We must leave the other process will execute normally, and only the process that calling us will execute our code. Of course, we execute code in the stack is an old exploit technique, but OpenBSD had a lot of protection in user mode. So we must take down all the protection, because OpenBSD wouldn't let us to execute code in the stack very easily. It got especially one protection that is called W-SOR-X. This protection says or implements that every portion of memory that is writable is not executable. So it's exactly what we want to do. We want to write in the stack and execute it. So we must take down this protection. This is something easy to do if you are in kernel, because this protection is implemented messing with selectors. Basically, with selectors are used in the Pentium 32 bits, and they say where a portion of the memory is executable and where is not executable. We simply, it's OpenBSD system, just fix or let's say they place the selectors in a specific pattern, and to prohibit, to let the process stack to be not executable. So we can change the selector because we are in kernel mode. So we just simply extend these selectors. These selectors are let's say, they mark a very little portion of the memory as executable. In fact, they mark just the first part of the memory as executable. So we simply extend the selector, and the act of extending the code, specifically this selector, the code selector, simply makes all the memory executable, including the stack, the heap, everything. So the system now is like, I don't know, Windows 95, because we can execute in every place of the memory. Now that we can execute in every place of the memory, we simply put the code in the stack and modify the return address to point to our code in the stack, and that is the next time that the system call execute and then returns to the stack of the process, and then it executes our code. Then, of course, we must restore the original interruption pointer, because if not, this gonna take this pseudocode, this portion of code will take over all the root process of the system, and that is not a good thing to do. We must take over only one process. So when we are finished take over the process, we restore the original int80 vector, and the OpenBSD kernel is running normally forever, let's say. It works perfectly forever. But now, the root process that calling us is executing our code in the stack. And now we can execute in user mode. That is much easier to do it than in kernel mode. In user mode, we can write things to the hard disk, we can make an internet connection, we can do everything. So, what happens if the process is not root? If the process is not root, we didn't do anything. We just continue with the original system call. So this hook acts only when the first system call from a root process is made. And if the system call is not made from root process, we didn't do anything. So here now we got our code executed in the stack in user mode. We say, okay, we are finished. We won, but we not won. This is a little complex. Why? Well, let's see. This is the drawing of how OpenBSD manage the memory in the Pentium 32-bit processor. Like I was saying, this portion of the memory is executable, only the low portion of the memory, because the code segment only reaches from here to here, and here are placed all the executable portion of the process, are the text section, and all the libraries are placed here. This is variable, it's not always 500 megabytes. The system moved this, but the important thing is that the heap and the stack is always in the non-executable part of the memory. And using this code, extending the selectors, we made all the executable. We really don't need the heap to be executable, but we need the stack to be executable because we are placing our shell code, our user code here. We extend everything. It really don't need to extend this, but we extend it anyway. It's easy. It's easier. Here is the part of the code. I'm sorry, it's a little hard to see assembler at this time of the morning, but here is the part of the code that implements the pseudocode that I was explaining in the other transparency. They are using little instructions that are not commonly seen in user mode. We got the local... in this instruction, we got the descriptor table. We find in the memory where is the descriptor table. In the descriptor table are the data about the selectors. Here is a little difficult to find because in the Pentium 32 bits, the selectors are like are not placed in one place. We must reconstruct them because they are placed in like mixed in the descriptor. In the descriptor, in every descriptor. No, sorry, not in every descriptor, but some of the descriptor got information about the selectors. We must reassemble the selector using this instruction. These are only shift and